Have you ever read a headline that just completely changes how you view the world? Like, even if it's just for 5 seconds.
Oh, yeah. Like those really bold declarative ones?
Exactly. Something like people who drink black coffee are 40% more likely to be psychopaths.
Right. Yeah. And I drink black coffee, so that one always gets me.
See, that's the thing. You see a statistic like that, and because it has a number attached to it, your brain just immediately registers it as an objective fact. I mean, numbers feel safe,
Yeah.
right? They feel precise.
We do. We just assume that someone in a white lab coat, pulled that percentage out of the universe using this flawless, unbiased machine.
Yes, exactly.
All right.
But when you actually look closely at the architecture of scientific research, specifically quantitative research,
Right.
you realize that, well, that machine is built entirely out of human choices.
Very human, very flawed choices. Choices that dictate who gets asked the questions, how the question is actually phrased, what environment the subjects are in, and crucially, what data just gets thrown out. That 40% more likely headline is really just the final coat of paint on a very complex and honestly, sometimes precarious methodological house.
Which is exactly why we're here. Welcome to the deep dive. Whether you are a student staring down a brutal methodology exam, or maybe a professional tasked with decoding one of those dense 100-page industry reports, or, simply a curious mind who wants to understand the invisible structures that shape our reality, you are in the perfect place.
Yeah, we have a lot to unpack today.
You really do. Today, we are taking a massive stack of sources. We've got academic guidelines, we've got philosophical methodology notes detailing this thing called the tree of knowledge paradigm, and these really deep analyses of sampling, study designs, and hypothesis testing. We were basically unpacking the machinery behind the facts.
Right, because we are dissecting how researchers attempt to impose order on a universe that is, frankly, fundamentally chaotic.
It's a mess out there.
It is, and the goal of this deep dive is to demystify quantitative research methods. We're looking at this not merely as, applied mathematics or statistics, but as a deeply specific philosophical lens.
So our mission today is to connect the dots between that underlying philosophy of science, the meticulous, granular way a study is constructed, and how those ultimate findings end up shaping the policies, the medicines, and, well, the headlines that impact your daily life.
Because it really does impact everything.
It does. But before we even touch a spreadsheet or calculate a single decimal point, we really have to start at the absolute beginning. We need to understand the worldview that gives birth to quantitative research in the first place. Academics call this the research paradigm. Like, why do human beings even bother trying to measure reality?
Well, research never happens in a vacuum, right? A paradigm is basically an overarching belief system, and it guides every subsequent choice a researcher makes. So to understand the quantitative paradigm, we have to look at the bedrock principle of modern science. It's a concept popularized by the philosopher Karl Popper.
Okay, Karl Popper.
Yeah, and the concept is called falsifiability.
Falsifiability. I mean, it's one of those terms that sounds like pure academic jargon, but it is actually the ultimate, bullshit detector.
That is the perfect way to describe it. The premise is remarkably elegant, honestly. Popper argued that for any theory to be considered genuinely scientific, it must be inherently testable. And more importantly, it must be capable of being proven wrong.
Okay, wait, proven wrong.
Yes. If a theory is structured in such a way that no possible observation could ever contradict it, then it isn't science.
That is so counterintuitive, though. You'd think science is about proving things right.
You'd think so, but a great way to visualize an unfalsifiable theory is to think about a generic daily horoscope.
Oh, I love this analogy. Okay, go on.
So you open the newspaper, right? And your star sign says, you will face an unexpected challenge today, but your inner resilience will guide you through.
Which feels super profound when you read it.
Right. It's incredibly sticky, but it teaches us absolutely nothing about the universe because it accommodates literally any outcome.
Because the parameters are entirely subjective.
Exactly. I mean, if you spill your morning coffee, well, that was the challenge. If you are laid off from your job, that was the challenge. If you get a sudden promotion, the challenge was, the anxiety of new responsibility.
So the horoscope can never actually be disproven. It's always right in hindsight.
Right. And because it can't be wrong, it doesn't help us learn what is actually right. Popper said that true science requires making risky predictions.
Risky predictions. I like that.
Yeah, a researcher has to stick their neck out and say, under these highly specific measurable conditions, X will cause Y. And if we run the test and Z happens instead, well, then my entire theory is incorrect.
They have to put their theory on the line.
Exactly. That risk is the engine of self-correction. By forcing researchers to operationalize their concepts, which just means they must define abstract ideas using strict, measurable terms. Falsifiability ensures that we are constantly weeding out incorrect assumptions.
Which leads us perfectly into the grand metaphor our sources use to break down this worldview, the tree of knowledge.
Ah, yes, the tree of knowledge.
Every research paradigm can apparently be deconstructed into 4 philosophical layers. So we are going to climb this tree from the roots all the way up to the branches just to understand how a quantitative researcher perceives existence itself.
Okay, so starting below the soil, down in the roots, we have ontology.
Ontology.
Yeah. Ontology asks the most foundational question imaginable, which is, what is the nature of reality? Does a singular objective reality exist outside of our human minds?
And for quantitative research, the answer is yes.
Right.
It's deeply anchored in a concept called realism.
Correct. Realism is the belief that the universe isn't just some subjective projection of our thoughts. Like a virus exists, it replicates and infects people, whether we believe in germ theory or not.
Right. Gravity warps space-time regardless of whether a human physicist is there to write down the equation. It's just happening.
It's just happening. Realism is that traditional route. But our sources highlight a really important evolutionary step in modern quantitative research, which is called critical realism.
Critical realism. How is that different?
Well, critical realism acknowledges that a definitive, objective reality absolutely exists, but it concedes that human beings are fundamentally flawed instruments.
Oh, I see. So the reality is perfect, but we are not.
Exactly. We have cognitive biases, our sensory organs are limited, and, our technology is imperfect. We know the virus exists, but our mathematical model of how it mutates is only as good as the microscopes and the algorithms we currently possess.
That makes a lot of sense. Okay, so moving from the roots up to the trunk of the tree, we encounter epistemology.
Right. And if ontology is the nature of reality, epistemology is the nature of knowledge. Basically, how do we go about capturing that reality? How do we actually know what we know?
And quantitative research leans heavily on objectivism here.
Yes, objectivism. This is the idea that the researcher and the phenomenon being studied are totally independent entities.
Like you place a thermometer in a beaker of boiling water. The water's temperature is not influenced by the researcher's political beliefs.
Right, and the thermometer does not alter its reading based on what the researcher hopes to find. It's just an objective measurement.
But wait, under that critical realism lens we just talked about, we have to update this, right?
We do. We update it to modified objectivism. We recognize that true 100% independence is, well, it's a mathematical idea.
It's not totally possible in reality.
Exactly. So we design double-blind studies, and we use algorithmic randomization to strive for maximum objectivity. But we know that perfection is like an asymptote. We can approach it, but we can never truly touch it.
Okay, so we've got the roots, we've got the trunk, which brings us to the sap flowing through our tree. Axiology.
Axiology. This one is fascinating. It deals with the role of values and ethics in the research process.
And historically, the strict, old-school, quantitative paradigm demanded that science be entirely value-free.
Totally value-free. The scientist was expected to be this detached, emotionless observer, just merely reading the output of the universe.
But this is where the philosophy has to collide with human nature, doesn't it?
Yeah.
I mean, being completely value-free seems practically impossible.
It is. It really is. The very act of securing a grant to study a specific disease means the researcher, or the funding board, places a higher human value on curing that disease over studying, say, the migratory patterns of a specific beetle.
Right. Just choosing what to look at is a value judgment.
Exactly. The choice of what to study, which variables to measure, and how to even frame the question, all of those involve inherent value judgment.
And that exact tension is what caused the massive philosophical shift from the positivist paradigm to the post-positivist paradigm.
Yes. So positivism being the old school approach. Think Auguste Comte and the early positivists. They believed in an absolute single reality that could be flawlessly mapped out through strict experimental designs.
They thought total objectivity and complete value freedom were actually achievable.
They did. But post-positivism is the modern upgrade. It is the operating system running almost all contemporary quantitative research.
So post-positivism embraces critical realism. It basically accepts that human bias is inescapable.
Right. Rather than pretending the researcher is some infallible robot, post-positivism relies on rigorous methodological design like causal, comparative, and longitudinal structures, which we'll get into to systematically trap and minimize those biases.
It replaces scientific arrogance with scientific humility. I love that framing.
It really does. We admit our fingerprints are always going to be on the glass, so we design the experiment specifically to measure and account for those smudges.
So this philosophical grounding directly dictates the final layer of the tree, which is methodology, the branches.
The branches, right. How do we actually conduct the work? And quantitative methodology is driven entirely by deductive reasoning.
Deductive, meaning we move from the massive and general down to the microscopic and specific.
Exactly. You don't just walk into a forest and start measuring random leaves hoping to somehow discover photosynthesis. You start with a broad theory.
And our sources define a theory as a coherent set of propositions that explains phenomena by specifying relations among variables.
Right. In practical terms, a theory organizes existing knowledge and predicts future events. And we usually split this into pure research and applied research.
Okay, what's the difference there?
Well, pure research simply seeks to explain how a mechanism works, like maybe mapping the neural pathways of the hippocampus.
Just knowledge for the sake of knowledge?
Exactly. Applied research takes that map and tries to solve a real-world problem, like developing a pharmaceutical intervention for memory loss based on that mapping.
Got it. But a grand theory is way too large to test in a single afternoon. To actually run an experiment, you have to deduce that theory down into a hypothesis.
Yes, the hypothesis. It is the critical bridge between the abstract philosophy we just discussed and the tangible data collection we're about to explore.
So what makes a good hypothesis?
A strong hypothesis has to meet several strict criteria. It must be specific. It must be empirical, meaning we can actually observe it in the physical world. It must be logical. And, circling back to our friend Karl Popper, it must be falsifiable.
Okay, to understand how this works in practice, let's build a running example for this deep dive. Let's say we are looking at this massive societal theory that the traditional 5-day work week causes widespread burnout.
Okay, good example. So that's the theory.
Right. Now we need to formulate the hypotheses to actually test it. And this brings us to what feels like a really fundamental tension in statistical methodology. The null hypothesis versus the alternative hypothesis.
This trips up so many people. So the null hypothesis, which is denoted as H0, is basically the statement of no effect. It claims there is no connection, no difference, or no relationship between the variables being studied.
So in our 4-day workweek study, the null hypothesis would state, transitioning employees from a 5-day workweek to a 4-day workweek produces zero difference in their measurable productivity output.
Exactly. It's the baseline of nothing happening. The alternative hypothesis, denoted as HA or H1, is the statement that the researcher actually suspects is true. It claims a significant connection exists.
So that would be employees on a 4-day work week demonstrate significantly different productivity levels compared to those on a 5-day work week.
Right. And the part of this that trips everyone up, and honestly it is deeply counterintuitive, is that researchers do not actually design their studies to prove their alternative hypothesis.
They don't.
No. They design their studies to reject the null hypothesis. We are basically trying to prove the negative.
That is so weird to wrap your head around. Why do they do it that way?
The reasoning lies in the mathematical nature of statistical probability. You simply cannot definitively, universally prove that a 4-day work week will always increase productivity for every single human being in every possible industry until the end of time.
Right, you'd have to test everyone forever.
Exactly. You cannot prove the absolute truth of the alternative hypothesis, but you can gather enough data to prove that the baseline assumption of zero difference is statistically absurd.
It's essentially the scientific equivalent of the legal principle, innocent until proven guilty, right?
That's an amazing way to think about it. The null hypothesis is the defendant sitting in the courtroom. The baseline assumption is innocence. No effect exists.
And the researcher acts as the prosecutor.
Right. The prosecutor's job is not to mathematically prove the defendant is a universally bad person in every aspect of their life. The prosecutor's job is to bring such an overwhelming mountain of data to the jury that the assumption of innocence becomes logically impossible to maintain.
Ah, I see. So if the data shows massive spikes in productivity across thousands of workers on the new schedule, the researcher hasn't just proven the new schedule works.
No, they have demonstrated that the odds of seeing this massive spike purely by random chance, if the null hypothesis were actually true, are astronomically low.
And this introduces the concept of the p-value, which I know everyone has seen if they've looked at a study.
Yes, the infamous p-value. The
Yeah.
p-value calculates the exact probability of observing your data, or something even more extreme, if the null hypothesis were entirely true.
So if your p-value is 0.01,
It means there's only a 1% chance you would see these productivity spikes if the 4-day work week actually had zero effect.
and because that 1% is so incredibly low, the jury rejects the presumption of innocence. We reject the null hypothesis.
Exactly, you've got it. And conversely, if the evidence is weak, say the productivity numbers are just a tiny bit higher, giving us a p-value of 0.40, we fail to reject the null.
Wait, we fail to reject. We don't just accept it.
No, we don't prove the null is true. We don't prove the 4-day work week does nothing. We just conclude that our evidence wasn't strong enough to convict.
Just like a not guilty verdict doesn't mean the defendant is definitively innocent. It just means the prosecution failed to make their case.
Exactly. The burden of proof wasn't met. We also need to specify if our alternative hypothesis is directional or non-directional.
Oh, right. Let's break that down.
A non-directional hypothesis simply states that a relationship exists, like a 4-day work week alters productivity. It doesn't commit to whether it goes up or down.
It just says something happens.
Right. A directional hypothesis actually points the arrow. A 4-day work week significantly increases productivity. You are predicting the specific nature of the relationship.
Okay, so now that post-positivist worldview is established and we have mathematically deduced our falsifiable hypothesis, we encounter the next major hurdle.
Yes, we need actual human beings to test this on. We need a sample.
Because obviously we can't implement a 4-day work week for every single employee on planet Earth just to see what happens. We have to select a smaller group that accurately mirrors the larger global workforce.
Right, and in quantitative research, the mechanism that makes this possible is probability sampling.
Probability sampling, what's the core rule there?
The defining mathematical rule is that every single member of the target population must have a known, non-zero, and equal chance of being selected for the study.
And this rule is basically the primary defense against selection bias.
Absolutely. Think about it. If you only survey employees at a trendy, well-funded tech startup about their feelings on a 4-day work week, your data will look wildly different than if you only surveyed assembly line workers at a manufacturing plant.
The contexts are just too different.
Exactly. To achieve generalizability, which is the ability to apply the findings from your small sample back to the massive population, you must utilize specific randomized techniques.
And the most foundational of these is simple random sampling.
Right. Simple random sampling is the ultimate lottery.
So imagine a corporation with exactly 10,000 employees. You want a sample of 1,000. You assign every single employee a unique ID number from 1 to 10,000, and you just run a computerized random number generator to pull exactly 1,000 numbers.
Exactly. Every individual has an identical 10% chance of selection. Statistically, this is the purest method because it allows the law of large numbers to just smooth out the anomalies.
If the sample is large enough, the random selection will naturally mirror the demographics of the company.
Yes. However, simple random sampling works best when the population is relatively homogeneous.
Right, what happens when the population is deeply fractured into specific distinct subgroups? Like if that corporation of 10,000 people consists of 8,000 entry-level staff, 1,500 middle managers, and 500 executives.
That's where things get tricky. A pure random sample might accidentally pull 0 executives simply due to the luck of the draw.
And if a key perspective is missing, the data is totally compromised.
Exactly. To solve this, researchers use stratified sampling.
Okay, I actually have an analogy for this one. Think of stratified sampling like assembling the perfect bowl of fruit salad from a massive disproportionate pile of fruit.
Oh, I like where this is going.
So if your pile is 80% grapes, 15% strawberries, and 5% kiwis, and you just blindly scoop a bowl using a simple random sample, the sheer volume of grapes means you are highly likely to get a bowl of nothing but grapes.
Right, the variance is too high, you miss the other flavors entirely.
Exactly. So to fix the variance, you stratify. You manually separate the population into distinct strata or buckets. The grapes go in one bucket, strawberries in another, kiwis in a third.
And then,
Then, you perform a random sample within each individual bucket, pulling a proportional amount from each. You intentionally select 80% of your final bowl from the grape bucket, 15% from the strawberry bucket, and 5% from the kiwi bucket.
that is brilliant. So applying this to our corporate study, the researcher manually divides the company into 3 strata: entry level, middle management, and executive.
And then, they randomly select 800 entry-level workers, 150 managers, and 50 executives.
Exactly. This forces the sample to mathematically reflect the exact architectural breakdown of the company. It drastically reduces the margin of error when comparing how different tiers of employees respond to a 4-day work week.
But both simple random and stratified sampling require you to have a master list of every single person in the population, don't they?
They do, and that's a huge limitation in the real world.
Like, what if you were studying the impact of a new agricultural policy on farmers across an entire country? There is no central, perfectly updated spreadsheet of every single farmer.
No, there isn't. And the logistical nightmare of finding and traveling to 5,000 randomly selected farmers scattered across millions of square miles, I mean, it would bankrupt the study before it even began.
So what do you do?
This is where cluster sampling becomes essential. Instead of zooming in on the individual, you zoom out to the geography.
You treat entire groups, or clusters, as the unit of random selection.
Right. So the researcher divides the country into, say, 500 distinct agricultural counties. They randomly select 20 of those counties. Then they send their field teams to survey every single farmer within those 20 specific counties.
The trade-off here is fascinating, though. You sacrifice a small degree of statistical purity because farmers within the same county likely share similar soil conditions, similar local economic pressures.
True. You lose some variance, but in exchange, you gain an immense amount of logistical feasibility and cost efficiency. It's a pragmatic, post-positivist compromise.
The final major probability technique highlighted in our sources is systematic sampling.
Yes, systematic sampling. This is utilized when you have an ordered list or a sequential real-world environment.
Right. You determine a sampling interval, often referred to as K. So if you have a list of 5,000 patients and need a sample of 100, your interval is 50.
You use a random number generator to pick a starting point between 1 and 50. So let's say it lands on 14. You select the 14th patient, then the 64th, the 114th, and so on.
This method seems highly efficient for field research.
It is. Imagine a researcher wanting to gauge passenger satisfaction at a major transit hub like a train station. They cannot randomly select from a list because the passengers are constantly flowing through the doors.
So instead, they stand at a turnstile and systematically survey every 20th person who walks through.
Exactly. But the major vulnerability of systematic sampling is hidden periodic traits.
Hey, what does that mean?
Well, imagine a manufacturing plant that produces a defective widget every 50th unit due to some rhythmic glitch in the machine,
Okay.
and your systematic quality control check happens to inspect every 50th unit. You will conclude the plant has a 100% failure rate.
Oh, wow. Or if you inspect every 49th unit, you completely miss the defective ones and conclude the plant has a 0% failure rate.
Right. The interval cannot accidentally align with a hidden pattern in the environment. So a rigorous researcher has to weigh the constraints of time, funding, and access when choosing their sampling method. And they must mathematically account for the inherent trade-offs of their choice.
Okay, so we have our philosophy, we have our null hypothesis, and we have our mathematically sound sample of participants. Now we have to build the actual laboratory. We have to look at quantitative research designs.
Yes, the blueprints of the study. And the overarching characteristics of quantitative design are determinism and reductionism.
Determinism meaning the assumption that specific causes reliably produce specific effects.
Right. And reductionism is the act of taking an incredibly complex reality, like human productivity or happiness, and reducing it down into isolated, standardized numerical variables.
Because you cannot just walk up to an employee and ask, hey, how productive did you feel this week?
No, you can't. You have to use clinically validated, standardized instruments. You measure keystrokes per minute, lines of code shipped, or revenue generated per hour. The design dictates how those variables are observed or manipulated.
And our sources break this down into several tiers of complexity, right? Starting with descriptive designs.
Descriptive designs are the foundational blueprints. They are explicitly designed to answer what is rather than why. They describe the current state of variables without any attempt to manipulate them or determine causality.
A prime example is the cross-sectional survey. This is basically a snapshot in time.
Exactly. You send a survey to 10,000 nurses asking them to rate their current level of burnout on a 1 to 10 scale.
You are capturing the exact prevalence of a phenomenon at one specific moment, but you cannot tell if the burnout is getting worse over time or what specifically is causing it.
Right. You are simply establishing the baseline reality. Moving one rung up the ladder of complexity, we encounter correlational designs.
This is where we start looking for relationships.
Yes. In a correlational study, the researcher measures 2 or more variables to see if they move together. But crucially, the researcher still does not intervene or manipulate anything.
We are just observing the dance.
Just observing. To find the relationship, researchers use statistical tools like regression analysis.
So a simple linear regression plots all the data points on a graph, for instance, hours of sleep on the x-axis and productivity scores on the y-axis.
And the statistical software then calculates the line of best fit. It minimizes the distance between the line and every single data point, which are known as the residuals.
The slope of that line gives us the correlation coefficient, ranging from -1 to +1.
Right. So a positive correlation means as sleep increases, productivity increases. A negative correlation means as stress increases, productivity decreases.
Our sources also highlight cross-tabulation here, which explores associations between categorical variables.
Yeah, cross-tabulations, you might cross-tabulate income levels like low, medium, high against the likelihood of owning a specific smart home device.
But we have to talk about the golden rule of correlational design. It's probably the most repeated phrase in all of science.
Correlation does not equal causation.
Yes. The classic illustration of this is the undeniable statistical correlation between ice cream sales and shark attacks.
Oh, I love this one.
Right. As ice cream sales rise in a coastal town, shark attacks rise simultaneously. If you only look at the regression line, you might logically deduce that eating ice cream makes you taste better to sharks.
Which is obviously absurd. The missing element is the confounding variable, in this case, the summer heat.
Exactly. High temperatures cause both an increase in ice cream consumption and an increase in the number of people swimming in the ocean. The variables are correlated, but one does not cause the other.
So, to definitively prove causation, to isolate the variables, and prove that the 4-day workweek directly causes an increase in productivity, you must leave observation behind entirely. You must use an experimental design.
Experimental designs are the absolute gold standard for establishing cause and effect.
They are. They require 3 strict conditions: manipulation of the independent variable, rigid control over the environment to eliminate those confounding variables, and the defining mechanism of true experiments, random assignment.
Let's break down random assignment because it really is the superpower of experimental design.
It is the magic ingredient.
So you take your carefully drawn sample of 1,000 employees. You don't just ask who wants to work a 4-day week.
No, because the people who want it might naturally be more motivated, which ruins the data.
Right. You use a random number generator to assign 500 employees to the treatment group they get the 4-day week and 500 employees to the control group they stay on the 5-day week.
The mathematical brilliance of random assignment is that it evenly distributes all the invisible, hidden variables between the 2 groups.
Because some employees naturally have higher baseline stress, some have better sleep habits, some have longer commutes.
Exactly. By randomizing the assignment, the laws of probability ensure that those confounding variables exist equally in both the treatment and the control groups.
So because the groups are statistically identical in every way except for the work schedule, if the treatment group shows a massive spike in productivity at the end of the study, you can confidently state that the schedule change caused the spike. Everything else was equal.
Exactly. You've isolated the variable. Now, within true experiments, the sources focus on several highly specific structures. The most common is the pre-test, post-test design.
Okay, how does that work?
You measure the productivity of all 1,000 employees before the intervention. That's the pre-test. Then you apply the 4-day week to the treatment group. Then you measure both groups again, the post-test.
This allows you to track the exact magnitude of the change within individuals, rather than just comparing end results.
Right. Then there's the distinction between subjects and within subjects designs. Our 4-day workweek example, as we just described it, is a between subjects design.
Because we are comparing the outcomes between 2 entirely different groups of people, Group A versus Group B.
Correct. A within subjects design takes a different approach. Every single participant is exposed to every single condition.
Oh, interesting. So how would that look?
Well, the entire company might work a 5-day week for a month, take a specialized productivity test, and then the entire company switches to a 4-day week for a month and takes the test again.
The major advantage there is that each participant acts as their own control group.
Exactly. You are comparing an individual's performance to their own past performance, which drastically reduces the variance caused by individual personality differences.
However, you must carefully manage what's called the order effect, right? Like, perhaps they just got better at taking the productivity test the second time around, so the numbers look better artificially.
Yes, order effects are a huge threat to validity within subjects' designs. Researchers usually use counterbalancing to fix that, where half the group does the 4-day week first and the other half does the 5-day week first.
That makes sense. Now, to really push the limits of complexity, researchers use factorial designs.
Factorial designs. This is when you want to test the interaction of multiple independent variables at the exact same time.
Let's say you don't just want to test the 4-day work week. You also want to test the impact of mandatory remote work versus mandatory office work.
Right. A factorial design crosses these variables. You essentially end up with 4 distinct groups. 4 days remote, 4 days in office, 5 days remote, and 5 days in office.
This allows researchers to uncover interaction effects. Maybe the 4-day work week only boosts productivity if the employee is also working remotely. Factorial designs reveal the nuanced, interconnected reality of the workplace.
They do. They model reality much better. But true experiments are not always possible, especially in the social sciences, education, and medicine. You frequently encounter scenarios where you simply cannot ethically or practically use random assignment.
Right. You cannot randomly assign 500 teenagers to smoke a pack of cigarettes a day for a decade to prove causation.
No, you definitely cannot. You also cannot randomly assign one classroom of students to receive a terrible curriculum just to see if they fail.
When random assignment is impossible, the researcher must step down to quasi-experimental designs.
Yes. The prefix quasi means resembling. A quasi-experiment resembles a true experiment because the researcher is actively manipulating an independent variable, but the groups are pre-existing. They lack the statistical armor of random assignment.
The sources outline something called a non-equivalent control group design.
This is a classic one. Let's say a hospital wants to implement a new, highly specialized hand-washing protocol to reduce infection rates.
They can't exactly randomly assign individual nurses on the same floor to use different protocols.
Right.
They would just cross-contaminate everything.
Right. So they implement the new protocol in the East Wing and use the West Wing as the control group.
The wings are pre-existing non-equivalent groups.
Exactly. The researcher can measure the difference in infection rates, but the internal validity is compromised. A critic could easily argue that the East Wing handles less severe cases, or maybe it has newer ventilation systems, and that is what caused the drop in infections.
Because without random assignment, you just can't be sure the groups were equal to begin with.
Right. Another fascinating quasi-experimental approach is the time series design. This relies on an extensive sequence of measurements over time.
Like, if a city changes its speed limit laws to reduce traffic fatalities, you can't exactly have a control city to compare it to.
No, you can't. Instead, you measure the fatality rate every single month for 2 years before the law passes to establish a really rigorous baseline. Then the law is implemented. Then you measure the rate every single month for 2 years afterward.
You are looking for a clear, undeniable interruption in the established trend line.
Yes, but you still have to watch out for historical confounders. Like, what if a new, incredibly safe car model was released the exact same month the speed limit changed?
Always something. The sources also mentioned the stepped wedge design.
Oh, the stepped wedge. This is a mixed factorial approach where an intervention is rolled out sequentially to different clusters over time until eventually every single cluster has received the treatment. It's often used in public health rollouts.
The final major architectural category we need to hit is longitudinal designs.
Yes. Within the post-positivist framework, time is a crucial variable. Longitudinal studies track the exact same sample of individuals over a prolonged period, sometimes decades.
It's the ultimate tool for establishing temporal precedence, which means, to prove causation, the cause must definitively occur before the effect.
Right. If you are studying the link between childhood trauma and adult substance abuse using a cross-sectional snapshot of adults, you have to rely on their flawed, retrospective memory of their childhood.
People's memories are terrible. But a longitudinal design enrolls a cohort of children rigorously measures their environment as it happens, and tracks them into adulthood.
It is the difference between trying to reconstruct a car crash from a single photograph of the wreckage versus watching a high-definition video of the entire event from start to finish.
I love that analogy. Okay, so to summarize the methodology so far, we deduce a falsifiable hypothesis, we draw a mathematically rigorous probability sample, and we funnel those participants through a highly controlled experimental or quasi-experimental design.
And the data is generated. The statistical software processes the p-values and regression coefficients.
The experiment is over.
Or
But a brilliant experiment that just sits in a desk drawer doesn't advance human knowledge. Science isn't science until it is communicated, subjected to brutal peer review, and replicated.
And the challenge is how to communicate these incredibly complex objective findings without the researcher accidentally injecting their own subjective narrative bias into the writing.
The scientific community solved this by developing a highly rigid, universally standardized reporting framework. If you open almost any original quantitative research article today, you are looking at the IMRAD structure.
IMRAD. It stands for Introduction, Methods, Results, and Discussion.
It functions kind of like an hourglass. It starts broad, narrows down to the microscopic data, and then broadens back out to the global implications. Let's trace our 4-day workweek study through the IMRAD anatomy.
Okay, so the introduction sets the stage. It reviews the existing literature, highlighting the gaps in current knowledge regarding employee burnout.
It builds a logical funnel that inevitably leads to the specific falsifiable hypothesis. A 4-day workweek will significantly increase measurable productivity compared to a 5-day control group.
Next is the methods section. This is the recipe. It is the architectural blueprint of literally everything we just discussed.
A researcher must explain exactly how the study was conducted and mathematically justify why they chose those methods.
Right. They must detail the sampling strategy. Was it stratified? They must outline the design. Was it between subjects factorial design? They must list the precise instruments used to measure productivity.
The fundamental requirement of the methods section is replication. It must be written with such exhaustive detail that a rival scientist on the other side of the planet could read it, rebuild the exact same experiment, and test the findings.
Because if a study cannot be replicated, it violates the core tenet of falsifiability.
Then we reach the bottleneck of the hourglass.
Yeah.
The results section.
And the rules for the results section are incredibly strict. It is pure, unadulterated data.
No storytelling allowed.
None. The sources explicitly mandate that there is absolutely no discussion, no interpretation, and no speculation in the results section. You do not explain why the numbers look the way they do.
You simply provide the statistical output, the tables, the regression lines, and the p-values. Productivity in the treatment group increased by 14.2%, p equals 0.003.
You just lay the raw materials on the table. The act of turning those materials into a meaningful conclusion is reserved entirely for the final section, the discussion.
The discussion is the so what.
Yes. The researcher interprets the results in the context of the original hypothesis. They answer the specific questions. Did we reject the null hypothesis? Does this align with the broader theory of occupational psychology?
They might conclude, the data strongly indicates that a compressed work schedule enhances output, likely due to increased recovery time. They are applying the microscopic findings back to the macro-level reality.
Now, the mechanical structure of IMRAD is supported by rigorous stylistic guidelines. Our sources specifically highlight the rules laid out in the APA 7th edition manual.
Quantitative writing must strip away the emotional persuasive language we use in daily life.
Right. You cannot write, the 4-day work week was an unbelievable, astonishing success that obviously proves everyone should stay home on Fridays. That is rhetoric, not science.
The language must be precise, objective, and measured. Instead of proves, a researcher uses verbs like suggests, indicates, or demonstrates.
It reflects the post-positivist humility we discussed at the very beginning. We are not uncovering absolute dogma. We are presenting the best possible mathematical model of reality based on current evidence.
One stylistic rule that absolutely fascinated me involves the use of the passive voice.
Oh yes, the passive voice debate.
If you read scientific papers from the 1960s or 70s, they are entirely written in this disembodied robotic passive voice. The participants were randomly assigned. The data were analyzed using a regression model.
Historically, researchers believed the passive voice enhanced the illusion of pure objectivity. It kind of removed the human being from the text entirely. But the APA 7th edition fundamentally reversed this. It explicitly encourages the use of the active voice.
So instead of the data were analyzed, the researcher writes, we analyzed the data.
Exactly. While the passive voice might sound clinical, it obfuscates responsibility. It hides the human choices that we established are central to the entire process.
The active voice, we assigned the participants, we calculated the p-value, promotes absolute clarity and enforces accountability.
It forces the researchers to take direct ownership of their methodological decisions. You cannot hide behind the machinery. You built the machine, and you are accountable for how it runs.
Which brings us to the final and, honestly, arguably most important component of the discussion section, the limitations.
Yes. Every rigorous quantitative study must include a comprehensive outline of its own flaws.
When I first encountered limitation sections, it felt incredibly counterproductive. Like, you spend a year gathering this amazing data, writing a brilliant paper, and then the final paragraph is essentially, here are all the ways we messed up.
It can feel that way, but the sources are careful to warn against an apologetic tone. Placing limitations at the end of a study is not a confession of failure. It is the ultimate expression of scientific integrity.
It is critical realism in action.
Exactly. It is the researcher saying, we sought the objective truth, but we recognize our tools are imperfect.
They clearly state that their quasi-experimental design lacked random assignment, so causation is suggested, but not definitively proven.
Or they point out that their sample was drawn entirely from tech companies in North America, which strictly limits the ability to generalize the findings to agricultural workers in Asia.
By meticulously defining the boundaries of their own claims, the researchers insulate the study against invalid criticisms. And more importantly, they provide a literal roadmap for the future.
They are handing the baton to the next scientist. Here is the exact boundary of human knowledge on this topic as of today. If you want to push the boundary further, here are the flaws you need to fix in your replication study.
It ensures that the tree of knowledge continues to grow, layer by layer, experiment by experiment.
Well said.
We have journeyed through an immense amount of architectural complexity today. We started deep in the philosophical soil of postpositivism, understanding that an objective reality exists, but our ability to measure it requires recognizing our own inherent flaws.
We explored the genius of Karl Popper and the absolute necessity of falsifiability, the mandate that science must make risky, testable predictions.
We observed how deductive reasoning helps formulate hypotheses, navigating the strict mathematical logic of assuming the null hypothesis of no effect until the data literally forces us to reject it.
We broke down the mechanics of probability sampling, revealing how simple, random, stratified, cluster, and systematic techniques battle against selection bias to create a mathematical mirror of society.
We charted the hierarchy of quantitative designs, from the descriptive snapshots of cross-sectional surveys to the correlational regressions that trace associations, all the way to the rigorous, randomized factorial control of true experiments that prove causality.
And finally, we decoded the highly standardized IMRAD framework that enforces replication, demands active voice accountability, and enshrines scientific humility through the transparency of methodological limitations.
It is, without a doubt, the most powerful system human beings have ever devised for attempting to extract objective truth from a chaotic universe.
But the system only works if we understand its parameters.
Precisely. And that brings us to the final provocative thought I want to leave you with today. We have spent this entire deep dive marveling at the incredible rigor of the quantitative machine. The math is sound. The sampling is precise. The experimental designs isolate variables brilliantly.
But the post-positivist paradigm admits that human bias is the ghost in the machine.
Human beings sit on the grant committees that decide which research gets funded. Human beings choose which broad theories to care about. Human beings formulate the specific alternative hypotheses that dictate exactly what the statistical software will look for.
So, the next time you scroll past a headline touting a new, undeniable, hard statistical fact, take a moment to look past the numbers.
Ask yourself, if the data we have is shaped by the hypotheses we choose to test, how much of our perceived objective reality is actually being defined by the questions society simply chooses not to ask?
A flawless calculation of the wrong variable still leaves you in the dark. The silence in the data is often just as structural as the noise.
Look closely at the numbers. Deeply respect the methodology. But never ever forget the very human architecture that decided to build machine in the first place. Thanks for taking the deep dive with us.